let's discuss the framework for the F-test. The hypotheses are, the null hypothesis is beta 1 equal to beta 2 equal to beta k equal to 0 against the alternative hypothesis at least one beta I is not equal to 0. Notice, of course, I didn't mention it earlier. We aren't interested in the constant term beta 0. We are always looking at the coefficients of the explanatory variables. We now define MSR as, if you recall, the regression sum of squares due to regression divided by k, and we define MSE as the error sum of squares divided by n minus k minus 1. Now, point is that, it's not quite part of our course, but the first one, MSR, is a chi-square distribution with k degrees of freedom, and MSC, I mentioned it earlier, is a chi-square distribution with n minus k minus 1 degrees of freedom. And one way of defining an F distribution is it's a chi-square distribution divided by another chi-square distribution. And that's where the F-test is coming. Now, point is this, that if H0 is true, then MSR and MSC are unbiased estimators of sigma squared. Already, if you recall, in the previous class, we said that MSE is a unbiased estimator of sigma squared. We also have MSR to be a unbiased estimator of sigma squared. But if H0 is false, MSR will overestimate sigma squared. But of course, MSE is always an unbiased estimator of sigma squared. Now that gives us a hint of what we need to do. It is that large MSR by MSE, large values of this ratio, implies that H0 is false. We can reject H0. And therefore, we're going to use the F-test, and it'll be a right tail test. That's because what we're going to have is, if this is my F-test, if I have MSR falling out here, very far away to the right-hand side, it means that MSR by MSE is very large. And therefore, we should be able to reject H0. Let's discuss the framework for a t-test. I have this estimate, y hat equal to b0, etc. is an estimate for the regression model, expected value of y equal to beta naught plus beta 1x, and so on. Now let's consider the ith independent variable xi. Now notice one thing. This bi, each of these b's are random variables. I take one set of sample, I'll get one estimated model. Tomorrow, if I take another set of samples, I'll get another estimated model. So each time I take a sample, my BIs will change. And therefore, until I have applied the least squares method and got the estimated model, I have no idea what these BIs are. And therefore, BIs are random variables. And we are making an assumption that because of the assumptions which we mentioned earlier, these BIs are unbiased estimators of beta I. Therefore, now if BIs are random variables, it must have a standard deviation, which I am denoting by SBI. I'm not interested in the formula for SBI, so let's forget about it. But there is an estimate for the standard deviation of the BIs. And SBI is an unbiased estimator for the standard deviation of the BIs. So now the point is that since I have an estimator, if you recall your hypothesis testing for means, what I have is that B1 minus beta 1 divided by SB1, for example, for the independent variable x1, will be a t-distribution. Of course, when you have a t-distribution, we should know the degrees of freedom. The degrees of freedom is given by n minus k minus 1. This is something you should remember, the degrees of freedom. And that's not too difficult. I mean, actually it is difficult, but the point is that this K, remember, is the number of independent variables. And this one is the constant. Where it's coming from is this, that in the estimated model, I am using my sample data to estimate 1, 2, 3, K plus 1 coefficients. So I'm estimating K plus 1 coefficients. My degrees of freedom will be the number of observations minus the number of coefficients I am estimating. And that's why I'm getting it as n minus K plus 1. And therefore now the test statistic, you got the idea, the test statistic from our hypothesis testing of means is going to be replace in my sampling distribution the value of B1 for this sample data. And this will be my test statistic. So then use this to test my hypothesis that beta 1 equal to 0 against beta 1 not equal to 0. So now when we test for, like I mentioned earlier, when we test for this against this, we say that we're testing for significance of xi. Like I mentioned earlier, I can also do testing for h0, where I do beta 1 maybe equal to 5, or maybe h0 beta 1 like greater than equal to 5, or beta 1 less than equal to 5. What we will do there is we will look at our Excel output, we will look at our confidence interval, and from there we will decide whether we should reject or not reject the null hypothesis in this case. And that we will do in the next class. I have mentioned this earlier and I'm mentioning it again. We must be careful about cause and effect. Just because we've accepted the regression model, that doesn't mean that there is a cause and effect. That cause and effect will only come from our domain knowledge of the situation. And that's what I'm saying out here. The point is that we may reject the null hypothesis, and we may say that, look, the relationship is significant. But we really should not conclude from this test that there is a cause and effect relationship. Just like I mentioned earlier about smoking and cancer. The point is that incidence of cancer and smoking are positively correlated. And therefore, if I do a regression, the regression will be significant. But the point is that till now, the medical the departments have yet to conclude that smoking causes cancer. In this class, we have discussed the testing ingredients for the F test and the T test. Thank you.